Yeah, thanks for inviting me along to present on this, Justin. My name is Adam Hall. I'm a PhD student at the Blockfast Identity Lab. I'm the OpenMind National Lead. OpenMind is a open source machine learning community. So we're trying to create privacy-preserving machine learning tools that are going to be open source and just free to use. I also work for a company called Edinburgh in Germany. They do privacy-preserving machine learning for healthcare. So yeah, OpenMind is a community focused on researching, developing, and elevating tools for secure, privacy-preserving artificial intelligence. And the Blockfast Identity Lab is a collaboration between a Hong Kong-based company called Blockfast, who do know your customer product on the blockchain, and Napier, who is the university this year, to sort of try and develop technologies which are going to protect consumers and their right to privacy online. So I probably don't need to convince you guys that the data industry is currently in boom. There's a similar sort of form of inflection as the crude oil prices from like the last century, only where crude oil extended our physicality by allowing us to sort of dig deeper or travel further. Big data sort of extends our intelligence by allowing us to make better predictions and do better medical diagnoses or optimize business processes. And there's a lot of potential for social good in with big data, particularly in the healthcare field. One of the first papers I produced was some work I did in my undergraduate as my dissertation. I developed a clinical decision support system that predicted the presence of type 2 diabetes in the childhood population of Glasgow. It was designed as a preventative tool to sort of be an online sort of screening application for people who may have diabetes who might want to get that checked without going into a GP surgery. And the idea is if we can make the data general enough and if we make the classifier accurate enough, we would actually be able to replace clinically invasive and expensive blood testing. And there's also big data for bad. I don't know if any of you are aware of Cambridge Analytica. Have any of you watched The Great Hack on Netflix yet? Great, this is all going to be very new to you. So, about 2 months ago, I was writing some slides to try and describe what's wrong with the data industry. And I wasn't quite able to put it into as good words as this documentary has. So I'm going to play to you the trailer, which will put this to you in a much better form than I ever could. Oh.
Who has seen an advertisement that has convinced you that your microphone is listening to your conversations? All of your interactions, your credit card swipes, web searches, locations, likes, they're all collected in real time into $1 trillion a year industry.
The real game changer was Cambridge Analytica. They'd worked for the Trump campaign and for the Brexit campaign. They started using information warfare.
Cambridge Analytica claimed to have 5,000 data points on every American voter.
I started tracking down all these Cambridge Analytica ex-employees.
Someone else that you should be calling to committee is Brittany Kaiser.
Brittany Kaiser, once a key player inside Cambridge Analytica, casting herself as a whistleblower.
The reason why Google and Facebook are the most powerful companies in the world is because last year data surpassed oil in value. Data is the most valuable asset on Earth. We targeted those whose minds we thought we could change until they saw the world the way we wanted them to. I do know that their targeting tool was considered a weapon.
There is a possibility that the American public had been experimented on.
This is becoming a criminal matter. When people see the extent of the surveillance, I think they're going to be shocked.
And I still fear for your life.
Yeah.
With the powerful people that are involved.
But I can't keep quiet just because it'll make powerful people mad.
Data rights should be considered just fundamental rights.
This is about the integrity of our democracy.
These platforms which were created to connect us
have now been weaponized. It's impossible to know what is what, because nothing is what it seems.
That was Cambridge Analytica, was they had asked a small subset of the American population to do a little personality test. And with the permissions from that, they were able to access these people's Facebook data. And not just their Facebook data, but their friends' data as well. And soon they were able to harvest all of the likes and so on, as you saw in like the previous trailer, until they had a good idea of who these people were. They would then create misinformation, and they would flood social media networks with this information to try and convert the people who were kind of on the edge or particularly susceptible to this kind of sensationalist information. And they were involved publicly in the Trump campaign, and then they were involved publicly in the Brexit campaign until they decided they weren't and refused to acknowledge anything about it. And they were actually also involved in around 10 other political events in countries around the world per year for the last few years. And this isn't the extent of how bad it gets with this kind of technology. It can get a hell of a lot worse. In 2018, after this whole Cambridge Analytica scandal came out and then they became sort of bankrupt, there was a similar kind of business going on. So I don't know how aware of the Rohingya crisis you all are, but yeah, it's been pretty terrible. And I've got like another wee 90-second video.
I call on the Myanmar authorities to suspend military action, end the violence, uphold the rule of law, and recognize the right of return of all those who had to leave the country.
Is a record of hard-right Buddhist nationalists on Facebook posting. So the red line is when the first state attacks happened against the Myanmarese villages. And we can see there's a very, very sharp upspike in the amount of misinformation and hate speech which is being propagated on Facebook before the attack. And then later on to continue the sort of justification for this attack. So it's not just our political agency which is at threat. People are being incited into violence through this technology. And it's genuinely terrifying. So, against that sort of backdrop and this sort of climate, there are some core things which the data privacy researchers want to preserve. And that's where we want to keep the original data values of data owners private, which is not present in current architectures because they've developed without the rights of citizens in mind. They've been developed to help big businesses make profit because that has been the only incentive through legislation until GDPR came out very recently. And they must also keep the model private to the researcher so that there's still a financial incentive for people to make models. And the entire system should be trustless. I shouldn't be giving my data because I trust Amazon with my data because they're a big company. I should know with cryptographic certainty that Amazon or Facebook can't then sell on my data to other people. So I want to give like a high-level sort of description around a few different machine learning architectures, mainly focusing around federated learning and several different flavors of it. And then talking a little bit about split neural networks at the end. So first of all, we'll go into a generic sort of deep learning process, just to give enough background to make the future bits make sense. So we have the most simple data set that we could potentially conceive of, and it's just an AND condition which we're wanting to learn. So we only get a 1 if both the previous conditions are true. And we can put the inputs into our X data and our outputs, which are the labels, into our Y data. We can then feed these X values into a neural network as a matrix, and that produces a set of Y hat values, which are our prediction. If we want to look a little bit more into what's actually going on during this forward propagation, we can look at the weights here and the biases, which are the actual parameters of the neural network model. We have the summation of these activations going into another activation function called the sigmoid function in this case to produce Y hat values, which are our prediction. We can calculate how well we've done in our prediction by comparing these Y hat values with the original label values using a error function. We then use this error function with backward propagation and gradient descent in calculus to work out which direction we need to step to make our model parameters perform better in future instances. Okay, so we have our original centralized learning sort of model. So we have a researcher, and we have Alice, Bob, and Carol who all have data. They give the researcher their data, so the researcher can then train the model. And at the end of it, the researcher has both the model and all the data that belongs to everybody else. And the researcher can sell the model to some businessman. But you might also sell the data, which is what sort of happened with Cambridge Analytica and Facebook. And not only that, he might actually lose the data as well. He might get broken into. And while this might not be too much of an issue in our country at the moment, in more authoritarian regimes, he could also leak information to the authorities, which could be fatal in some cases. So it's not very good for Alice, Bob, and Carol. And it doesn't really satisfy our privacy preserving machine learning conditions. So we need to keep the data values private, which we are not private. The model of the researcher is kept private, so that's okay. And the system still needs to be trustless. So federated learning is one of the most popular privacy preserving machine learning architectures at the moment. And instead of the researcher giving Alice, Bob, and Carol, Carol giving the researcher their data, the researcher gives their model to Alice, Bob, and Carol. Alice, Bob, and Carol all train separately, and they produce gradients. The next step is they need to go to improve the model. They can then send those gradients up to the researcher, who aggregates them and or averages them and creates a new model. Which researcher can then sell the model without selling any of the data. But then Alice, Bob, and Carol don't really get any money out of this. And the researcher's model can get stolen because he just passed the model to Alice, Bob, or Carol, or Eve in this case, to train in plain text. So let's say Eve is at the very, very end of this training cycle, and then the model is almost at professional level or like industry standard level, then they could just steal it, and there's nothing really the researcher can do. The researcher can also analyze these gradients that he gets passed by Alice, Bob, and Carol in order to reverse engineer the original values of the data. So, in its current form, the vanilla federated learning doesn't really work for any of our privacy constraints. So, introduce homomorphic encryption. So, homomorphic encryption is where we can encrypt two different things, let's say a 3 and a 5, and we can still perform mathematical operations on those things. So we could take these two ciphertexts, what would have been 3 and 5, to create 8 if we have them together. So we can actually encrypt the parameters of our model to create a homomorphically encrypted neural network which actually still works. So we do the same process. We train the models that are now encrypted at a computational overhead. And then we're left with these encrypted gradients. We can then send the gradients back to the researcher who decrypts them with their public key, and then they have a model. But they can still... But the researcher can still reverse engineer the gradients because the model is encrypted, but it's encrypted with their public key and their private key, so the gradients are still in plain text to the researcher. The researcher could also just encrypt the model that he sends across. Well, there's no guarantee that when the black box model that the researcher sends across isn't just a Trojan, isn't just reporting the data values back to the researcher in some way. So this is another difficulty. So yeah, the model's private to the researcher, but we still don't really have our privacy constraints reached. So we can have secure aggregator federated learning, which is where, again, we have the researcher sending the model out, training, gradients, and then instead of sending it to a researcher, we send it to a third party. Third party then averages these gradients and then sends that to the researcher, who then decrypts the model. The researcher doesn't have access to the model before it gets averaged, so then he can't know what the individual gradients are, but the third party does, and he could still collaborate with the researcher to reverse engineer the gradients. The researcher wouldn't necessarily be able to steal the model, though, because the researcher, so the third party wouldn't be able to steal the model because the researcher is the only one with the private key. So it's still not trustless. So we have a multi-party aggregator. So we have Alice, Bob, Carol, and Dave, all process, and then they flip a coin. And instead of sending their gradients to a third party, let's say the guys who get tails elect somebody who got heads to take their data. So the guys who got heads then would receive gradients. So then Bob and Carol, who had been this subset, could then average the gradients that they received, and then they flip a coin. And they just continue doing this until there's only one aggregator remaining, who would be Carol. Carol then sends it off to the researcher, who then decrypts and has the model and can make cash. But then we need to rely on the researcher not being a member of the training pool who receives gradients. So now we have secure multi-party aggregator. And it relies on this concept. We have this simple arithmetic, which is 8 plus 15 creates 23. But instead of sharing it in that form, we can split it up into shares. So we can split the number 15 up into 3, 5, and 7, because they create 15. And 2, 3, and 3 would be then the 8. We can then distribute these shares of the original information. And then 3 plus 2 is 5, 5 plus 3 is 8, 7 plus 3 is 10. And if we add these three together, then we still get the same answer. So similarly, we can distribute the model. We can train, we can then get the gradients. But instead of sending the gradients back to just one person, they can split their gradients into shares and send one share to each person. And these third parties need to collaborate in order to get the right answer at the end of this. But no one party has the original gradients. And then the third parties can then add these together to send to the researcher. The researcher can then unencrypt the model, and we're fine. This is pretty much trustless. This is as trustless as we get. This is the open mind stack. So this is something that I've been working on, and it's slightly more recent than federated learning. The genesis paper sort of came out at the end of last year, and instead of taking one neural network, copying it, and sending it away multiple times, you take a neural network and then you split it into segments. You then send the segments off to Alice, Bob, and Claire. So then Alice, who has segments 1 and 2, and then also 5, in this very, very small example, Alice can put her X values to the first segment and create an output, and feed that output directly into the next segment, which goes into the third, and the fourth, then the fifth, until it gets to the end layer, and we get our actual prediction. We can then compare this prediction against Alice's labels, and then feed gradients backwards through the segments, and update along the way. We actually transition the signal from this loss equation back through each segment by taking the activations and the gradient of the corresponding activation and just dot joining them together and then doing a summation. That creates a new loss function for each segment layer. So we just send these back, do this computation at each layer, and we can update this model as if it was just one cohesive model. We then do that for Alice in process. We do the same for Bob, but we pass him the start and the end of the model. We do the same thing for Claire. So they've all had data and they've all trained, but no one has a full idea of what's going on. They just, at any one point, have either the start and end layer with their data, or they're just taking part in this big multi-party computation. Once they've finished training on all the data sets, they aggregate these together and then send it back to the researcher. So next I want to talk a little bit about OpenMind. We're having a meetup at the end of the month. If you're interested at all in any of this and would like to get involved, then please come along. There's a lot of ways that you can join our community. Just join our Slack. It's growing by the day. Our GitHub is fairly expansive, but there's plenty of issues to jump on board on. You can join the local Slack channel, there's one in Edinburgh. You can take the free course, which is run by Andrew Trask, who will be coming to Edinburgh at the end of the month for the Edinburgh Napier Crypto Conference. And yeah, thanks for listening. Cheers. Hand over to you, Justin. So there is actually, and it's something I'm working on at the moment. So when Alice starts off, she has full knowledge of segment 1. And then she'll send it back and she'll update. And then she sends segment 1 to the next person to train. So she sends segment 1 and 5. If Alice has knowledge of segment 1 when Bob trains, then Alice gets the activation signal and knowledge of the model. She could potentially reverse engineer Bob's data values. So my current approach for dealing with this is either to homomorphically encrypt the entire model, which is not really a good thing because it's highly computationally expensive. But there is something to be said for distributing that computation amongst multiple workers. Alternatively, there is an approach called differential privacy, which I've not covered in this. But the idea is when you're updating weights, you add a little bit of noise. You reduce you take a half of the average change that you would make and apply that to all of the different parameters, and you add a little bit of noise, so it's very, very difficult to figure out which data came from the X, or what data produced the activations which Alice would receive. So how do you mean?
So if you apply a little bit of noise, so all the values you're putting in, some go up, some go down, and then at the end of the day, the up and down should all
ideally, but but that's not the way it's been designed. But that would be great if it did. It's mainly just it does reduce the accuracy of training and accuracy of predictions just slightly. Well, there's actually a parameter which you can tweak depending on whether you want privacy or you want less noise. But yeah, is there any other questions? So how do you mean when one's going to be added? So is this in terms of applying homomorphic encryption to it? So there are fully homomorphic encryption schemas, and there are also different frameworks which will flip between using one homomorphic encryption schema and going to a nonlinear approximation. So I've not looked at the Google alternative which you mentioned, but I'd be up for hearing some more about it later on. All right, okay. Yeah, so that's one of the massive downsides of not being able to see data that you're training a model on. You need to rely on the data being complete, like trustworthy, and without blemishes. But if you can rely on that, so like for example, if Alice, Bob, and Claire were to be 3 different hospitals, each with a data science department who wanted to train on each other's data without breaking any GDPR rules, then this would be. But yeah, you couldn't just take randomers data on self-regard and trust.
There's a few might instigate an answer there. As Bob and Claire could be hospitals, so actual departments. But I was really thinking also how are Alice, Bob, and Claire actually running this? Is OpenMind a platform kind of like SETI, so that here install this and let it do the chunking, or is it sort of this is the package that gets deployed to institutions and they act as Alistair Bob?
So OpenMind is still very much unfinished. At the moment, we have socket workers and we just have virtual workers who would be Alice, Bob, and Claire, just to prove that the architecture works. But the final product is still very much in development.
It's not like the idea that's being proposed is sort of research institutions saying, hey, here's our software that we model on this principle. It's more flat as a platform. I'm more concerned about like, people running code.
So as in, so I'm not sure I understand the question.
Is it software or is it a specification for anyone to write software for?
So it's software primarily. So this portion of the project is called PySift, which is the bit to do with creating sort of the architectures, which is and it's sort of backbone is PyTorch. But there is another aspect of the project called Grid, which is about connecting people with data, with who would have, let's say, data on a farm somewhere, which they were willing to lease out to these algorithms. About connecting people with data to researchers. And that's currently being worked on by, yeah.
Cool. In developing these models, like practically speaking, is it one of the considerations that you come up with the best trade-off between encryption and how complex the model is, like the process of the data?
Yeah, absolutely, yeah. Because homomorphic encryption, while I've talked about it quite flippantly here, it's hugely computationally expensive. And there are other ways that are not necessarily homomorphic encryption, which you could get this thing that being done, like namely like secure multi-party computation. That's what's used by OpenMind at the moment mainly. Yeah.
You had a slide of good data and a slide of evil data. I just wanted to ask you your position on good data rendered without fear because it's good data. But you've got age and postcode. So how does age and postcode be good data?
So I meant like big data implementations that are for social good. So like healthcare is an area where we could like. Absolutely not. That's the sort of information which should be kept on your device, or which should never actually leave your hands or your custody.
Or even don't collect.
Oh well, yeah, but we would still like to be able to make a prediction with the information which that postcode would provide. But it's whether we make it on our end on our server, or we send the model out to you for you to perform it. We shouldn't take. Why should we take a postcode if we can't ever see it? So it's not particularly useful to have just a pure postcode. But with our model, we linked that to the Scottish Index of Multiple Deprivation. So we had quintiles based on the deprivation linked to these postcodes. So instead of using feeding a postcode to the model, I would feed a score between 1 and 20. And what we found was the places with higher deprivation had higher incidence of diabetes. I don't know if that was it. I'm just talking about like a publicly created data set that which correlates postcode to. I mean, it could have been used in other research, but I couldn't speak for that. Is there any other questions?
Is it this model? Is it just a theory, or do you have code written for it?
I did actually. Second. So there's that sort of explanation which I talked about in the slides. So this is the original research, or this is from the original research which was created, I think. And it's actually meant to be a lot less computationally expensive than federated learning and large batch stochastic gradient descent. But if you want to see an example of it working, I tested it against just like a normal centralized model, which is here, and over 3 batches on the same data.
If you could speak about the downfalls of it and things that you're working on right now that can improve it.
Yeah. So I was going to run that.
What are the challenges?
So this is it actually working. This is passing the model locations. And then again. And this is a final prediction. And I think I lost it. Yeah. Lost it in there. Yeah, anyway. So there basically you can reverse engineer that first segment, which means somebody who comes first in that training process can then reverse engineer everybody previously. So that's currently like a problem that we're trying to solve with our architecture. And there's the option of going down that on a home market encrypted path, which is quite computationally expensive. And there's also option of doing differential privacy, which I've not talked about here. But yeah. I will show you the biggest data set I've tried this on. It's absolutely tiny. No, this is more just a proof of concept at this stage. The plan is to benchmark this against eminence. But that's once we have the thing at a stage where we feel like it's secure.
I suppose if a new model is if a new model is being developed, right, and there's no sufficient data yet to come up with even like a good predictor, like at the starting phase, then like how does this method work?
So this is just a way of splitting up the model. The model itself should behave identically to any previous model. So we just use a very, very simple one here. But it kind of doesn't matter whether the model itself is a good predictor. All that matters in this is whether it can still learn in the way that it would if it was centralized.
Two questions about the practical proof. The first question was about that. Do you validate the results of training sets out against traditional approach to see that actually the same thing falls out?
So that's literally what's happening in this tutorial. So I know you can't really. I didn't plan on showing this tutorial as it is in its current But at the very, very start of this tutorial, we do a non-distributed training example, and we compare the training on the same data. And it's almost identical. It's trains a little bit more slowly with the split neural network, because there's obviously the network involved. There's like latency between sending stuff places, and yeah, but it's same. It's almost the same model being trained.
Yeah, I guess that's sort of my next two questions about the durability of the role, something large scale. What would you expect this to be possible in apps with tens of thousands of users? That would be my first question. And the second question is, it seems to me that there's a bit of a trade-off here. That you do get certain hardening of encryption for distributing knowledge, but at the same time you send a lot of things back and forth. So that all that added encryption wouldn't principle make it possible. No encryption is usually that. So how would you expect that trade-off to be balanced in a real world example? If you think that's
Well, so I think there's going to be that trade-off between how secure you want it and how computationally expensive it's going to be. But I think you're saying we want to harden things by distributing the data, but we also want to be careful of which data we put onto the network, because then that can be taken advantage of. Right. So I think it's more to do with just making sure the data that we send across has been sanitized properly, or has at least been encrypted in some way, or is at least on its own so useless that it's impossible to do anything with. I mean, we would obviously be using TLS between each individual sort of agent, so that only that agent would be able to see what was sent on the wire, theoretically. But yeah.
When you're saying the more users you have, the more secure it becomes.
This particular example, yeah.
I can follow up to this question. Not sure if I understood what I meant.
All right.
Is that at the starting phase of a module, how do you get the participants of the certification if they know that like the model is not good yet, like there's not enough sample size for it to
So there'd be two ways that people would interact with this model. One way would be the predictions, which I wouldn't expect them to try and get a prediction off of this model if they knew that the sample size was too small. And the other way is they can train it. So I would expect people to train it if they knew the sample size was small. And that would continue until it got to a point where the model was proven to be good enough that it would be validated on some third-party set, which was either differentially private or like secure or valid in some way.
So in one word, would you say that this model is still applicable for newly developed prediction models?
I'm not sure. So this is a method of training a network. So yeah. So yes, it is.
It is also a method of developing the model and fine-tuning.
Yeah. So that's essentially what this architecture does. Is it develops these gradients through a distributed training process as opposed to a centralized one. Devastating. Yeah, there needs to be proper user validation. So yeah, it would work in a case of hospitals where we can validate people's inputs, but it wouldn't necessarily at this stage, without other privacy controls or without other security controls, work on an individual to individual basis, because I could start gaming the model if and start putting in things which would make me invisible to it in some way. I'd adversarially influence it. Everyone, thanks.
We'll send some of those links out via Twitter so that if you want to go take a look at the detail in your own time, you can.
Right. Sorry, switching MCs for a bit. So, yeah, I think that was it for Edinburgh Tech Meetup August edition. I don't know if Justin mentioned, but this event basically is sponsored by Skyscanner, Informatics Ventures, and used to be Cultivate, but they were bought out by Deliveroo, so now we're sponsored by Deliveroo. With money, not food, but yeah, if you want to give a talk next month or in the times to come, Justin's. Yeah, if you would like to give a talk in October, come talk to me or Justin or Tiggs. But for the time being, I think we're gonna thank you everyone for turning up, and we're gonna go to the Blue Blazer, which is at the end of the road, to continue the conversation and I guess have a few drinks. So yeah, thank you very much for turning up, and hopefully see you the next month. Thank you.